All right, guys, Mr. Antonucci here, and we're going to continue our discussion on the limits of trig, exponential, and log functions with determining where trig functions are continuous. I want to check out the graph of sine and cosine in Desmos. Here I have the graph of sine x, and in blue, we have the graph of cosine x. And from these two graphs, it appears that sine and cosine are continuous on their domains, which is the set of all real numbers. Now, to show that sine is continuous at x equals 0, first we need what the value of f of 0 is. So sine of 0 is equal to 0. And then we need to take the limit as x approaches 0. So the limit as x approaches 0 of sine x and is equal to 0. Now, by the definition of continuity, since the limit and function both exist and are equal to the same value, then cosine is said to be continuous at x equals 0. In a similar way, we could show that cosine of x is continuous at x equals 0. Now, a theorem that we have here is the sine function is continuous on its domain, which is all real numbers, and the same thing is for cosine. Consequence to that theorem is since they are continuous at all real numbers, then the limits exist and can be evaluated by direct substitution for all real numbers. Also, the other four trig functions as well as the 6 inverse trig functions are all continuous on their domains, which is important to know because not all of the trig functions have domains of all real numbers, just sine, cosine, inverse tangent, and inverse cotangent. All the other ones have restricted domains, but on those domains, the trig functions and inverse trig functions are continuous. Next, we want to talk about where exponential and logarithmic functions are continuous. Another one of the theorems for exponential and logarithmic functions is that exponential functions are continuous on their domains, which are all real numbers, and a logarithmic function is continuous on its domain, which is all positive real numbers. And then another consequence of this is that the limit for an exponential function can basically be evaluated using direct substitution as long as that c value is in its domain. And similarly, for evaluating limits of logarithmic functions, you can evaluate them using direct substitution. Now, there's a couple other limits that should be familiar from pre-calc. The limit as x approaches negative infinity for e to the x is 0. That's the left end behavior of e to the x. As x approaches positive infinity, the limit of e to the x is infinity. In other words, that's the right hand behavior. As x approaches 0, the limit of e is 1. Now, if we move to the natural log, as x approaches 0 from the right, the limit is negative infinity. As x approaches 1 at 0, and as x approaches infinity, the limit is infinity there as well. Wanted to hop on to Desmos just to show you that as x approaches negative infinity, the left-hand behavior, the y value of e to the x approaches 0. And as x approaches positive infinity, e to the x grows without bound. And also at x equals 0, the limit and function value both equal 1. Then if we pull up the line y equals x and reflect e to the x over that, we would get the natural logarithmic function. The limit as x approaches 0 from the right would be negative infinity, because the domain of log is all positive numbers, so you can only approach 0 from the right. As x approaches infinity, the limit would be infinity as well, even though it grows very, very slowly. And as x approaches 1, the limit is 0. So here's a couple examples. We want to show that e to the 2x is continuous for all real numbers. Now I have the graph here in red of e to the 2x. In order to do this, we need to consider the domain of this exponential function. The domain of the exponential function e to the 2x is x such that x is a real number. That implies that f of c equals e to the 2c. So the domain is all real numbers. For any number c, the limit as x approaches c of f of x is equal to the limit as x approaches c of e to the 2x we can rewrite e to the 2x as e to the x squared. And there is a power property for limits that says you can take the limit as x approaches c of e to the x squared, and then that limit is equal to the limit as x approaches c of e to the x, that limit answer squared. And we know by the theorem up here that the limit as x approaches c of a to the x, in this case we're using base e, is a to the c, or in our case, e to the c. So this would be e to the c squared, which is e to the 2c, which is equal to f of c. So since the limit equals the function value for any number c, then f is going to be continuous for all real numbers c. Now we want to tackle this one. We want to show that g of x equals the cube root of natural log x is continuous for x greater than 0. So the graph here in blue suggests that it's continuous for x greater than 0, but we need to analyze it. So if we let h of x equal natural log x, that's the basic natural log function. We know that is continuous on its domain, which is x greater than 0. That's one of the theorems we just went over. If we let m of x equal the cube root of x, since this is x to the 1/3, we know that this is continuous for all real numbers. If we let g of x equal m of h of x, which is going to be the cube root of natural log x, then that composite function is continuous for x greater than 0. So the original function is continuous for all real numbers x greater than 0. For both of these examples, we were basically trying to find what are the basic functions that are being used here and what kind of combinations are being used to produce this function, and how does that relate to the limit properties that we've done. So that's it for this one, guys. Hope that was helpful to you. Take care.